So that's my Suno. The Suno is here. So let me continue like what we talked about type class. So again, like the idea is to extend the idea of typical sequences to like beyond typical. So you have not just like typical and non-typical sequences, and you think of like there are some sequences and those are non-typical, can be in different types, and the type is simply defined as like the empirical distribution of that sequence. So in the sense like the sequences, two sequences to be same type will be like they have the same empirical distribution. Say like if I'm folding a coin, tossing a coin, then the typical two typical sequence in the same class, type class, will be like they have the same number of head and same number of tail. And we talked about last time like some of the bounds for like typical sequences, not typical sequences, I mean the type classes. For example, like first of all, like we have like we say we have some distribution P. Maybe I change color to have a new page. So say we have a type class P. So basically like that sequences have the empirical distribution P, and then we define the type class as like TP, right? And then like for that TP, we can we show at the very end is like the size of the type class is bounded by it's bounded by 2 to the n h p. That's basically the number of sequences in this type class is upper bounded by like 2 to n h p, and then it's lower bounded by like 1 over m plus 1 x 2 to n h p. So this is like the size of the alphabet of the source itself, and of course it's just the length of the sequence. And also like we have some bound for, let's say, the number of typical or number of type classes. We define, I think, a script P. I forgot like how do I notate that. Let's see. Yeah, I denote that like as something like that. P and X is all the possible types with alphabet X, with random variable X, and also like the length n. Then the size of this, basically the number of types, different types will be bounded by n plus 1 x, something like that. So the let's see, what else do we have? And of course, like if I have a sequence, like let's say if this let's say xn or just x is in this type P, then the probability of this x to occur is just like 2 to n x. It's exactly 2 to n x. Wait. Is that, oh no, wait. It cannot be. That's the one that is like the typical one. That should be equal to. Wait a sec. 2 to the n is exactly 2 to n 2 minus n h p plus the Carroll divergence between p and q, where q is the true distribution of x, and p is the empirical distribution because x is belong in the type class P, right? So that's more or less what we show, I guess, last time. And yes.
What is the p extended? The biggest, you mean that upper bound of that?
You mean this one here?
Yeah, I mean that's in the middle.
Yeah, this is the number of sequences in that type P. Right?
Here.
Typecast P. Oh, okay. This one is the number of typecasts.
Oh yeah.
Yeah.
The size.
Yeah, the size, like number of typecasts. Yes. Let's
For
see
the
if
particular.
still no one there. I'm not sure. It's just some technical problem. Let me see if there's any email from anyone.
If you send the email.
Yeah, I think I sent it. Let me just make sure I send it. I think I just sent it. Yeah, this is I just sent it, right? Okay, that's nothing yet. So that's so far we have proof, and then now let's see what else we want to show. And then we want to show, okay, the last thing we want to show is basically what's the probability to get a sequence of type P. So know the difference here, the difference between this one and this one. Oh, okay, like I got mentioned here. So so the difference here is we are saying that we have a particular sequence that belongs to type P, and we are asking what's the probability to have that sequence. But here instead, we are asking what's the probability to have any sequence belong to type P. Then of course that will be just simply bounded by this one multiplied by the number of sequences, right? So therefore, it would be just bounded by yeah, because the number of sequence is the type P, right? Because that's the probability that you get any sequence belong to type P. And this is we got a sequence in a particular type P. So this one should be just simply will be the probability of this, because it will be the same, right? Once the sequence is belong in type P, the probability will be the same. It's just equal to this one multiplied by the number of sequences in this one, right? So this is actually what I want to say is this is just equal to 2 to the minus n h p plus kl p times q. That's the probability to have any sequence in type P multiply the number of sequence in P, right? In type P, right?
Why? Because that is because the particular that's and then that's.
This is you have, let's say, I ask you what's the probability, if I'm floating a coin, let's say I have a type maybe n is equal to 5, let's say, right? And then I can have a type, it's type T 3 2 that represent that I have 3 heads and 2 tails, right? Then the probability of getting a sequence head tail particular sequence is equal to this, basically confirm something like that.
Yeah, that's right.
But if I ask you what's the probability to get any sequence with this type, with this particular type, then will be that means that what's the probability to get head tail, or head tail head, or head tail head, so on, right?
Yeah.
That would be just equal to the probability, this probability multiplied by number of sequences you have in that type, multiplied by this, right?
Oh yeah, that's right.
And this is bounded by this guy, right? So therefore, like probability TP will be simply bounded by like this multiplied by this guy is just equal to 2 to the minus KL P and Q. And oh, I miss an N here. And also like 2 to the.
So you already calculated that.
This is what we showed last time.
Oh yeah, last time.
Yeah, that's what we showed last time.
And then you calculate that. I mean that you input to there.
Yeah, I just substitute this into here, right?
Substitute to there.
This the probability here is the same, right? Probability
Yeah.
of each sequence is the same. It's just equal to this guy.
So that will be cancel that for NHP, cancel for that, and then just only KL.
Yeah, NHP will be cancelled. Yes.
Yeah, and then that's
PQ over m plus 1.
yeah, that's right.
Yes, something like that. So that's it. That's more or less all what we want to show. Basically, that the tools we were going to use is like how many type classes we have is bounded by this. And note that like this is much smaller than like on any other things like we occur like all these bounds, because this is like n is large, x is kind of small, so it's like polynomial of n only. This one is like exponential of n, right? And we are interested in like number of type classes, how many sequences in each of the type class, and also like what's the probability of a sequence in a type class given by this, and what is the probability to get any sequence in a type class is bounded by this, basically.
I'm still forget about
Which one?
That's mean that for particular the size for particular this one. The bound for particular size, that's for particular
Oh wait. This is not. This is the number of type classes.
number of type classes.
Yes. For example, like you have type n equal to 5. You have type like 3 head and 2 tails, right?
That's right.
You also have a type like 4 head and 1 tail.
That's right.
A type like 5 head and 0 tails, and so on, right?
Oh yeah.
There's so many types that is bounded by like n plus 1.
Oh,
Yes.
yeah.
That we showed last time. Yes.
For all of n.
Yes. And that's what we have. Let's see if I miss anything here. Yeah, I think I have everything here. So, yeah.
What is the correlation between that and that?
Which one?
Correlation between this and this actually. It's mean that this is just for to get the probability and then just to get the size. So there is a correlation.
No, we are not using this way. I don't know what you mean by correlation now, but here we didn't actually use this here directly. We use this bound here,
Yeah.
but actually when you show this bound, we can't use this here. So you see this term here.
Yes.
When we show this one, we use this. But for this one here, it's very simple. Right? We are basically saying that for each sequence in the type, all the probability is the same. Like this, we can show it. Like I actually showed it last time, and it's exactly equal to this. Unlike for typical sequences, when you are in the same type, it's exactly equal to this. This is a pretty obvious, right? Because you have sequence of the same type with the same number of heads, same number of tails. For example, like your toes and cons, then the probability would be just the probability of a head to the power something and the probability of tail power something. So all of them will have the same probability. And then we show like in one type, for a particular type, the number of sequences is bounded by this, upper bounded by to the NHP and lower bounded by this term here. So therefore, if we put in this into here, then we just have this way.
Yes.
So therefore, like to your question, I'm not sure like when you mean correlation, you can say like it's pretty have an indirect correlation because we show this bound within using this, but when we show this, we don't actually directly use this. Yeah.
So that is for bound.
Which one? The second one, the first one?
Type class is just for bound.
Type class is this. Yeah, this is number of type classes. It's just a bound.
Yeah, that's bound.
We use a bound because we said that we can compare exactly. It's basically actually it's exactly something like if I remember correctly, let's see. N factorial over let's see. I forgot like oh no, actually it's not this one. But this one we can count it, right? We can count it. This is like yeah, but anyway, like you can go back to the last class. But we don't care about this exact value anyway. We're only interested in like a bound like this because this is sufficiently small comparing with other terms here.
Yes.
Yeah. So okay, so let's continue. With what we like to talk about today is that we want to see some application for this method of type. So first thing I like to talk about is like the so-called a universal source coding. So if we remember what we talked about like pretty early in this course, we talk about like source coding and wait a sec, can I flip back? And basically we have a source that we try to compress that. We can compress up to the entropy of that source if we have a discrete memoryless source basically. Defined by some distribution, so this is like something discrete, and it's like memoryless in the sense that when you draw a sequence like x1, x2, x3, all of these are kind of independent to one another, and so we kind of talk about, we show that like how we can approach that. For example, like we said that we can, I guess we didn't mention Huffman coding kind of, but also we talk about Shannon alias code as what? How is that? Shannon alias? Yeah, I think it's SF equal Fano SF equals Shannon and Fano alias code. So as an example, that using that we can approach the capacity HX. So we can design a code to, but for those design, for example, using Huffman coding or using SFE, for both of them, like you need to know the source statistics. You need to know the PX to actually design the code. So when we say this universal source coding is something like, how about we don't know the source statistics beforehand. For example, think of like you have this very common, you either using Ziv or like RAR, so on, like compressed file.
So no need to know about PX.
We don't actually, right? When you use that, we don't actually know the PX. Of course, you can say that like maybe it kind of estimate the PX beforehand, but actually they don't need to do that. So the question is like, if I don't know the source statistic here, can we still achieve the can compress up to this theoretical limit matrix? So that's the question. Like, can we reach this? Can we reach this even if we don't
Because
know
for having that should
px?
yeah.
For Huffman, you mean?
For Huffman,
Yeah, for Huffman, you will need to know the px, right?
yes.
So, but let's look at some theoretical proof first. Like afterward, we will give an example, like of universal source coding, how you may do it in practice. But let's look at the theorem. The theorem is saying that like we can actually do that. So for any source Q, like let's say the source Q, that this is the distribution of that source basically. As long as I have like some weight is bigger than HQ, then there will be, I can compress a length n source. So it's basically the same setup of FP as previous, but just that we don't need to know this kind of statistics of Q. We don't actually need to know the distribution of Q. And we can still compress, that's still lossless source code. And we don't know this. So how we're going to do it is like the following. So we have a proof for that. So first we'll define Rn as R minus x times log n plus 1 over n. This is something magical, but let's say we define Rn as this. So what you can see is that as n goes to infinity, Rn will be just approaching R, right?
Yeah, that's right.
Yeah. So that's the whole point. We design.
Infinity.
Yeah.
That will be 0.
Yeah.
So
Okay. Let me write it better. This, if this go to infinity, I guess I need to use an eraser like this. Then Rn will approach R, right? So now we design a code book A. That's basically a very simple code book. It's like we're going to assign a code or assign just an index for any sequence that satisfy that your type of that sequence is less than Rn. So let's kind of think in like what we have here. So we consider like any sequence, any particular sequence. We look at the type of that. That basically Pxn is the empirical distribution of that xn, right? As long as the empirical entropy is less than this Rn, then we'll kind of assign an index for this xn here. So notice that here we don't need to know the actual distribution, right? We didn't use
that is not typical sequence. This is not the
this is not typical sequence. Typical sequence is you have close to 2 to the minus n tricks, right?
Yeah, that's right.
So close to 2 to the minus n tricks. Here we are saying that like we have a sequence and we look at the type class and the entropy of that type class, or sorry, not the entropy, I mean we look at the distribution of that type, the empirical distribution of that sequence. The entropy of that one is less than some Rn, less than the Rn, then we will include in the code book. Yeah. So then encoding will be something like, if I look into the code book, right? Look into code book. For example, if I have given for example, if I like to, I have input, I compress Cn, let's say, or x hat n, let's say, or x tutor n, x tutor, maybe just x tutor. Then if x tutor is inside A, then I will output index, right?
Yeah. Still inside A.
If it's not, then it's failure. We just, okay, we don't know how to do it. I mean, we just fail. Then,
So this means that it's not in that A.
then if decoding is nothing, right? Just map back, right? So if it's not failure, then it's okay because the code book is 1-to-1, right? So if decoding, like actually I will just say trivial here, right? So if like I actually receive the index, there's no failure. If I actually receive the index, I'll just go back to the code book and see like which is the actual sequence that.
So we already know the mapping one to one.
Yes, the mapping is a.
Just we already know the code book.
Yes, the mapping is 1-to-1. So it's just like you list all the sequences satisfy this in this A, and then the first sequence you put like index 1, 2, 3, 4, and so on.
Yeah.
Now let's check the weight of this code book here. I will claim that the weight is less than less than R.
How
What?
we will not find that is not in the code book? That is mean that error.
If it's not in the code, okay, we will talk about that. So we'll worry about it. But first, we didn't show that like this is actually. We say this is a scheme, right? But we want to show that first for this particular scheme. Wait a sec. Yes. Okay. Yeah, as you asked, how about the probability of failure? We will study that afterward. We want to show, of course, the probability of failure is very small, so we can ignore that. But before that, we want to look at what's the weight of this scheme here, because we established such a scheme here. Right? What we want to show is we hope to show that this weight is pretty close to R, or actually we can show that this weight is less than R. So then in that case, we use this scheme here. We're saying that there's some scheme that acts on. I don't know why there's this line here. Let me. I can't even erase that for some reason. Anyway, so we want to show that there will be some of this universal source coding scheme, such that if the weight is larger than this HQ, then there will be lossless compression, right? Now
Actually, rate
yes.
is the original rate for that source.
The rate is the original rate of the source.
Yeah, that's mean in there the definition of R. The original rate.
Actually, the rate here, you should think of the size of the code book, right? Because you have incoming sequences. when it's in the code book, you have an index sending out, right? So you're basically you are using a length and sequence. I mean, or I should say, like you compress like a length and sequence, right? And then like for this length and sequence, you use this code book have like the size of the code book is like, let's say A is the size of I sketched that this is the A of the size of the code book. Then the weight for this A, there's so many number of index, you will need log A so many bits to store it, right? So therefore for length and sequence you need so many bits, so therefore the weight is actually something like log A over n, right? Something like that. Yeah, that's the weight, right?
And then this bigger than entropy of that.
That weight should be bigger than the entropy, but at the same time I don't want that to be like very big. Actually precisely I hope that like to be like close to HQ, right? So I want to show that this is arbitrarily close to HQ. Otherwise, that would be useless, right? If I'm proposing, okay, this scheme here, turns out the scheme actually have a weight is like 2HQ, then it doesn't show anything, right?
How to make sure that will be close to it?
Now we're going to see like what is the weight here. So, but first of all, like, let's look at like what is log A over n here. Log A over n. This is stuck here. Or maybe let me start with like A. Let's see what is the size of A here. The size of A will be equal to all the type classes. So consider all the distribution P. We say that like we will have A is basically with all the sequences that have the empirical distribution. I mean the entropy of the empirical distribution is less than Rn. So therefore like we will consider all the P, all the empirical distribution P for HP less than Rn, and that will correspond to some type. And for this particular P here, we can consider a type there, and that type will have like this so many sequences, right? So therefore you add them all together will be the size of A, right?
But why it should be times by PI?
PI? Which way? No, this PI.
In here.
This is not PI. I'm not writing PI. I mean, sorry, like this is a bad handwriting. It's just saying that like this sum over P, all the P. This is so bad. Sum over all the P, the distribution P, such that like HP is less than Rn, right? And then like for those distribution, then you consider the type class there. The type class have so many sequences, and you add all those sequences, number of sequences together. That would be the size of A.
Yeah, that's right.
Yes, and then like this is bounded by, because we know what's the bound for the number of type classes that we have that earlier. Actually, just a page earlier, something like if the number of the above, like this is bounded by 2 to NHP, right? So then we just say, okay, this is bounded by 2 to NHP, so therefore this is bounded by 2 to NHP, sum over P HP less than Rn, and
it should be less than also.
It's less than equal to less what?
And there is less than also at the bound.
Here? Yeah, it doesn't matter actually.
Doesn't matter. Then it's just for upper bound.
Yeah, it's less than. Yeah, it's less than. It was upper bound. Yeah. I mean, if you don't like the equal sign, you can. Yeah, but let's keep the equal sign. I forgot like whether. But then this one is less than. Wait. Do you still have problem with this one? Like, wait.
I mean that.
Yeah.
Okay, could you scroll up?
Yes,
Because
yes.
there is, we have two, so you
Yes,
want
I
to
have
see
this.
from this one, and then you not include for this
No,
one?
no, I don't care about this one. I don't care the lower bound.
Lower one.
I don't care. No, because I just want to show like what's the size of A is bounded by something, upper bounded by something. I want to show like A eventually. The size of A is bounded by something.
Oh
Yeah.
It's less than something.
Yeah.
Okay.
So then this is upper bounded by this, and then I can continue this because what HP okay, and from the definition here, right, HP should be less than Rm, right? So therefore, like this is sum over P, HP, Rn, 2 to the n, Rn, right?
And Rn.
Yeah.
Why this part?
Because you are summing over P, all this P is supposed to satisfy this condition, right? HP is less than Rn.
That's right.
Yeah, that's therefore this way. HP is less than Rn. Okay. HP, this is of course your exponential function is monotonic, right? So if you are if you have like x less than y, then 2 to the x will be less than 2 to the y, right? Just like that, right? Yeah. So you have like HP is less than Rn, so therefore 2 to the HP is less than 2 to the Rn, right? 2 to the nRn, right?
Oh yeah.
Yeah.
That's right.
So then this become a constant, right? Again, like we use this kind of trick lots of times. So this is constant. We can pull out of the summation. We have 2 to the n Rn, then sum over P HP less than Rn, n times 1. So that would be like just counting. What is this doing? This is counting the different distribution, right? But this will be like less than, because this is counting the type classes that satisfy HP is less than Rn. But then of course this will be less than the total number of type classes, right? Total number of type classes.
For all classes, not only one.
This one is basically counting the type class. The type classes satisfy this one, right?
Yeah.
And then of course this will just include like some particular type classes, and that will be less than all the possible type classes, right?
Yeah.
And we know the bound for all the number of type classes. This one is bounded by n plus 1 to the x, right? So therefore, like this will be bounded by n plus 1 times x, 2 to the n Rn.
So actually, it is not depend summation. We can take it to the outside.
Yeah, this does not depend on. This is Rn, right? Rn is a constant with respect to P, right?
Yeah.
Here we are summing over P, right? This does not depend on P.
Oh yeah, that's right. Yeah. That's all. And then responded. Okay.
So then I can write this to be like 2 to the n Rn plus x log n plus 1 over n. So this is basically rearranging the terms. Like this become like 2 to the log. This is like 2 to the log n plus 1 x, right?
Yeah, that's
Something
right.
like that. Then my x can go down here, and then like
Yeah, x and
more like
and
let me look for the n here.
yeah, I think n should.
Oh,
be
n is here.
outside.
N is here because n.
N should be outside. not
Yeah,
inside.
n is outside. Yeah, you're right. N should be outside. Yes, that's right.
Yeah.
Yeah. Then this is it, right? And then we know that that's why we have this weird definition for Rn. we define at the beginning Rn as this way. So therefore, like these things here is actually just R.
Yeah.
So
This
those,
is not negative but positive at there.
yeah, no. This if you go back here, I'm flipping too fast. This is like Rn equal to R minus this. Therefore, R is equal to Rn plus this guy here.
Oh yeah, that's
Yeah.
right.
Yes.
So that is R.
So this is R. Yes. So in conclusion, that you have A is bounded by 2 to n r, right? So therefore, like, actually the weight, as we say, that the weight should be equal to log a time over n, right?
Yeah.
So it's bounded by log 2 to the n r over n. That's basically just like equal to r. So the weight is bounded by r.
This one from where?
Uh,
And
from here, a eventually is bounded by 2 to the nr.
yeah, that's right.
So therefore, like, weight is equal to log a over n.
Yes.
So it's bounded by log 2 to the nr. So this is a is bounded by this way, bounded by 2 to nr.
Oh, this one you put this into the R. So you
Yes, this
you
is
can
r.
put
Yeah,
that.
yeah,
So and R. Oh yeah, that's
yeah. This is here 2 to nr, right?
yeah, that's
Yeah.
right.
Yeah.
So and divide by n. Yeah, become yeah.
Yeah, that's yes. So therefore, like, the conclusion is that the weight here is bounded by r. We'll use that later on, but here, let's go back to your earlier question. You say, how about the probability of failure?
Yeah.
So the probability of failure,
That's that.
yes.
So we find R, we find that, right?
We find the
R,
we have the yes.
and we
With the weight is bounded by r first, but we are not there yet. So we are be patient. We are not there yet. We are going to use this this result here is that the weight is bounded by r. And now let's just first show this. Like, the probability of failure hopefully is kind of small. So note that the probability of error is what? The probability of error is basically equal to, or the p
It's E more than I.
right? Because I remember, right, what is A? A is defined as all the sequences such that, like, let's see, all the sequences such that, like, the empirical distribution has entropy is less than Rn, right?
That's right.
Less than equal to Rn, let's say.
Yeah.
So then, like, everything like outside this I cannot code it, right? So therefore we just look at, like, everything that's outside that then we look at, like, everything outside that will be just summing over the type classes that is outside A, and we see, like, what's the probability of those type classes, and we add them all together. And this one will be bounded. Again, we want to upper bound the error probability. So we want to show this error probability will be kind of small. So this is PH, P bigger than Rn. And what we can do here is, we can upper bound this by the maximum of all this guy here, right? So we can look at, like, all the possible P that satisfy this condition here, like H, P bigger than Rn, and we just see, like, what's the maximum of this. So of course, if we pick the maximum, this will be bigger than that. Then again, because we pick the maximum here, Now this guy does not no longer depend on P, right? So again, we can pull this out actually. So this is equal to the maximum P HP bigger than Rn probability TP and sum over P HP bigger than Rn times 1. Again, this is kind of counting the number of type classes that satisfy this condition, right? Then, of course, this will be upper bounded by all the possible type classes.
So it means that there's no depend to the P. Meanwhile, in here P actually. So
this does not depend on P because you are taking a maximum of something. You are taking a maximum value. Let me give you an example again. Like you just say, I'm summing over I equal to 1 to 5, let's say, right? Sum over this, let's say, and then I say okay, what's the maximum of from 1 to 5? That would be this is bounded by I equal to 1 to 5, right? Can I say that? Right?
Yeah.
This is kind of silly, but I can do that, right? And then this 5 I can pull it out, right? Because this 5 the source depend on this index I, right? This is exactly the same like here.
So it means that already now that will be 5, 4, 5 I, because that's this in here I is always the bigger in here.
I'll just take a bigger one, or you can put for example some function like fi in general. Then I will say the maximum of this function maybe some value, the maximum of that.
Yeah, that's right. So you just
maybe I tutor, right? And then this will not depend on this index anymore.
Yeah,
then I can pull it out. Yeah.
Pull it out. That's right. Oops.
Yeah. So so then let's see. Then same argument as before. This one is the counting the number of type classes satisfy this particular condition, right? So this will be upper bounded by the total number of type classes, and then will be upper bounded by just say m plus 1 to the x, right? That's what we know earlier on. Yes.
From the earlier.
Yeah, from the earlier.
Yeah, okay.
So then this guy I can write it another way. Again, I like to write it as actually what I can use is I can probability of TP we know from earlier. Let's see, probability TP, let's go back earlier. Probability TP is upper bounded by this guy, right? Yeah.
Yeah, that's right.
So let's use this bound here. So therefore this one is bounded by 2 to the n 2 minus n KL P2 to Q or something like that, right?
So because you only got that the upper bound.
Yeah, I only care about upper bound. I want to see what's the.
So you
the
don't care about lower bound.
No, I don't care. The probability of error I want to be as small as possible, right?
Yeah.
As I show that the probability upper bound by some values, and that values goes to 0, then it's done, right?
Yeah,
Because
right.
probability of error cannot be negative. So and this I can write this as another way as 2 to the minus n minimum P tutor HP bigger than Rn KL P tutor Q. So because if this exponential is minimized, then this thing is maximized, right? Because I have minus sign here. The smaller of this guy, the larger this guy here.
Oh yeah, so you make on the logarithmic that.
Yes, this is 2 to the n something, right? To the n log. So of course I
take it minimize that.
yes, because I'm maximizing here, I should minimize here. and I don't want to forget this one also. I still have this n plus 1 x, and now what's going on is we have let's see.
So we should minimize we can take out the n plus 1, 2 outside. First.
Oh, wait. We don't.
There is no p on there.
P?
That's right. Yeah. There is no p right in there. So
No, there's a P. There's a P here. This is P tilde here. You cannot pull out.
Pull out there to there.
No. Oh, yeah, sure. This is outside. This is not the.
Yeah, we cannot take the.
I mean, this you can put here. No, this is not inside the exponential. This is separate.
Oh yeah.
This is this term here, and this
Oh,
is
yeah,
this
yeah.
term here.
Oh, yeah, that's fine.
It's just the product of these two terms here. Now let's go back what we have really. Remember that we almost get lost at what our goal here. So we start with the theorem. We're saying that like, we have some source Q here. We don't know the statistic of this Q. We only know that HQ is less than R for some R. That means that the weight is like bigger than this one that we're trying to and then we have this R, so we start with like define this R and using this R. So remember we have this condition here. So that means that like we actually have a condition that am I here? Yeah. I think I still have, yeah. I have a condition that HQ is less than R. Okay. It's less than R, right? This is like what we have from the question itself. So we from the very beginning HQ is less than R. But
But this is not less than R. It should be bigger than R.
HQ is less than R.
But in this case, HP bigger than R.
Yes, that's the contract. HP is bigger than Rn. It's like different, right? So yeah, you're right. Actually, that's exactly we are using this. So Rn is approaching R, right? As Rn as n goes to infinity.
Yes.
So then it means that like for sufficiently large nr, for example, like if I can from some n naught, so as long as n is bigger than some n naught, so combining this and this, I must have like HQ is less than Rn, right? So basically I have this Rn continue to increase like close to this R, and I have HQ is somewhere here, right? Because HQ is less than R. Then if I have this is this point, probably this point I call it n naught. So whenever consider I have n is bigger than this n naught, I will have this Rn will be bigger than HQ.
And n will be going to infinity.
Yeah, n is going to be infinity anyway.
So that will be go to the Rn less than Rn. That's right.
So therefore, what's going on is I have well, okay, I get confused myself. I have okay, all this P here. Yeah. Okay. What?
That is Q, not P.
Yeah. That's Q. Yeah, that's Q.
This is Q. Also.
Yeah, that's Q. Yeah, this is Q. What?
This one also Q. That's right.
Oh yeah, this is Q. Yeah, this is Q. It's not P. Yeah.
So that should substitute to that.
Let me write better. Like I have exist some n naught such that if n bigger than x naught, I will consider n bigger than n naught, then I will have like h.
What's n more in there? Actually.
N naught is somewhere here. So somewhere. So as I let me clear.
That is new.
Because I have Rn, I have Rn, I have some R here, right?
Yeah.
And basically, like your Rn will continue to increase,
Mm-hmm.
and
Going
eventually it
up.
will approach R.
Yeah.
Right.
And opposed to infinity.
Yes, and also I have like some HQ here. This is HQ because HQ has to be less than R, so it'll be like that. So at some point, like at the beginning, like my Rn can be less than HQ.
Mm-hmm.
But at some point, like maybe I call this n naught here.
Mm-hmm.
For all n bigger than n naught, Rn will be bigger than HQ.
For all n.
For all n bigger than n naught,
all n.
Rn will be bigger than HQ.
Oh yeah, that's right.
And then like let's look at say, so consider those n. Now consider in those n. So what I have will be Rn is bigger than HQ, and HP is bigger than Rn. So that means that P and Q cannot be the same, right?
Sorry.
Yeah, okay. And for those n, like for those like n bigger than n naught,
Yeah,
we have Rn bigger than HQ.
that's right.
And here, like I have this HP, or like HP tutor maybe like HP tutor is bigger than Rn here.
Yeah.
So therefore, this HP tutor like has to be bigger than HQ. So meaning that like P tutor and Q cannot be the same, right? Or like because like this P tutor is bigger than Rn, and then this Q HQ is less than Rn. So P and Q cannot be the same. That's the whole point.
Yeah, that's right.
So
This
PM
means HP theta is bigger than HQ. HP theta is bigger than HQ. That's
yes,
right?
yes, and more importantly, just they are not the same.
Mm.
And they are not the same, then like KL divergence has to be positive, right? KL divergence is basically saying that like to measure the difference between two distributions, and they will be the same. I mean, they will be okay. This will be equal to zero only when they are the same, right?
Yeah.
So this will be non-zero, basically. The whole talk about all this is just saying that this cannot be
Yeah.
zero.
Can
So
be zero.
this is non-zero. Then that's okay. Like then I have this n goes to infinity. This will be go to zero, right? Even though I have like n to the something, but this is only polynomial of n. This is exponential of n minus n. So therefore, this value will go to zero, right? Yes.
This one is not same because not same. It means
Yeah.
that not going to zero. It will be one or all of this will be positive.
Yes,
because
this
not
is
same.
positive. Yeah.
So when you say that is positive, so why you say that should be zero?
Oh no. This has nothing to do. I mean the whole term will be zero. This
Why?
is a 2 to the minus exponential something non-zero times times n plus 1 to the x. As n goes to infinity, of course this will go to infinity. But this is a polynomial of n only, right? But this is a exponential of n. So therefore, this thing as a whole will go to zero, right? This will go to zero faster than this one will go to infinity, basically.
Oh, yeah, that's
Yeah.
because this will be bigger than this one.
The 2 to n something
Yeah,
will be
right.
bigger than this one.
Yeah.
So when you're 2 to minus n something will be like,
will be zero.
much faster. So this will be zero.
Faster. Oh,
So therefore, like the probability will go to zero. So that's the whole thing we would like to say about it.
so
The
there is
prob-
no failure. I mean, there is no,
The failure will go to zero as long as your n goes to infinity. The failure will go to zero.
we cannot find some nominal value. I mean, that how much or the probability of error.
No, we don't care actually.
So all of this will be zero. Will be go to zero.
We don't care. We will all go to zero. And
But we can find that. We can calculate that for some n. not to infinity. For n maybe 10,000 something like that. We can calculate that probability of error. That's right.
No, we don't care actually. That's the point. Like we only care that like okay, we have a scheme here. This is kind of okay. Again, like other proof in like information field, like source coding, that the one we saw earlier, for channel coding theorem and so on. We don't actually care about the probability of error, the exponent of that. We just care about like it actually goes to 0 as n goes to infinity, and that will show that like we can achieve the capacity, right? And this.
But we cannot don't know how much n should be infinity. That's right or not?
No, the probability of error is going to 0, but let's go back to the weight of that code here. What's the weight we showed earlier? I got a little bit confused myself. We show that the weight is actually less than, the actual weight is less than R, right? And that okay, actually we already finished the proof, because what we start to say is like we want to show that there's some universal coding. Let me summarize the whole thing again. So we want to show that there's some universal source coding approach, that we have some discrete memory like source Q here. We don't know the statistic of this Q.
But in here,
Yeah.
this condition n should go to infinity. In one we don't know infinity is. I mean that this is 10,000 is infinity, 1 million is infinity. So we
No,
don't know.
that doesn't matter. That's the whole point. It's like calculus, right? We don't care about like how big this is. Like we just say okay, if we make it like sufficiently large, then we can achieve that.
Oh.
Yeah. And
So that
but be very careful. Like it doesn't. Okay, this is not. We are not cheating here to have infinity, because I remember, for example, in channel, this only for example just in this case here, even you allow n goes to infinity, if your weight is less than this entropy of this Q, still you cannot compress it, right?
yeah, that's right.
Yeah, you can compress it just because your weight is bigger than HQ here, and also we here like we don't need to know the statistics of Q here, and to just summarize the proof again, like basically we introduce some proof that construct a codebook like this, right? And we show that like with this codebook, basically we just say if we encode, you just look at the sequence whether it belongs to the codebook, then we send the index. If not, we just say failure. And the code will be trivial, right? We receive the index, we will show if there's an index, we will just recover that and it will be lossless. And then we show the probability of error is equal to 0, right? As long as your n goes to infinity, probability of error goes to 0. Earlier we showed what's the weight. The weight for this scheme here is actually bounded by R, right? We go through quite a bit. You can actually bounded by R. So it means that like we already we kind of already proved that, because we say that okay, you have this scheme here. We set a R would be anything is bigger than HQ, and then we design a scheme that the rate is actually less than this R. We didn't say whether it's bigger than HQ or not, but this rate is definitely less than R. And then this scheme actually is able to get like lossless compression. Like the error the failure rate is equal to 0. Yeah. So
the point that we should find that's R here, the A, the typical sequence to find code books.
No. I mean, this is done. This is
for practical.
For practical, it can be totally different. For practical, like I'm not sure how much you can borrow from here to get an idea. Like for practical, maybe like you can design a scheme maybe similar. It's like you just look for type classes that you only, but in practice, I'm actually going to give a practical example, but it actually doesn't use idea like this. For example, if you look at idea like this, I may sort out all the possible sequences like with different type classes and look at only type classes is bounded by some RN here. But the problem is that you have n goes to infinity, right? And then only doing this is computationally impossible, right?
Yeah, possible.
Yeah, so therefore, like in practice, people don't do that. So, but this is just a theoretical saying that like you can achieve that, like in theory.
Yeah, that's right.
In practice, you are not going to do that.
It means that no need to calculate the entropy of Px and no need to know the HQ here. Just
In practical, most likely not. Yeah.
Yeah, just find some A.
No, actually, in practice, even not. Like maybe I just give one example here, like a practical, like very simple. Some like I just give an example of like universal source coding. It's the Lempel-Ziv.
This is used for.
Yeah, this is I no, I don't. I think it's a sieve and so on, like PK-Ziv. Yeah. So Lempel-Ziv, like or like that's the main idea. Like of course they have variation. After so many years, they have like modification and improvement. But the basic idea is still more or less the same. So for example, like let's say I'm going to compress a bit stream like this. Like let's see. 1 0 1 1 0 1 1 1 0 1 1 1 1 0 1 1 1. Let's say I'm going to compress a bit stream like this. So what we are going to do is we're going to input.
Oh, the input.
Like this is it's a binary bit stream. I'm going to compress it. So what I'm going to do is I'm going to parse segment and segments, like one segment at a time. So and whenever I see a new kind of segments, I just kind of like put it in a new group or something. So more precisely, let's say I look at like start from the beginning. I pass the first digit here. So and the first bit, let's say, is 1 here, and I never seen 1 before. I would just say like 1. I'll create a kind of like code book, something like. I would say like my first code book have a 1, and I'll index it with 1. And then in the next step, I look at the second bit here, and again I didn't see a 0 before. Then I will say introduce a new code book, a new code of 0, like, and put an index 2 here.
That is 1 and 2 is code book.
The whole thing is code book. This is like a code word. You can think of it as code word.
And 1 and 2, what is that? The index?
Yeah, the index of the code word. Yeah, of the code word. So then for the next one, you see 1. Okay, I see 1 before, right? I see 1 before. But I didn't see 1 before. So I will put 1 1 as a whole and index that. So I have 1 1 index as 3.
Okay.
So then I continue. Let's say I look at 0. I see 0. Yeah, 0 before the 0 1 I never see before. So I see 1 as 4. And then I have like
1 already know.
1 1 no, but 1 1 0 I don't know. So I 1 1 0 I index as 5. And then I have 1 1 1. Yeah. 6. And then I have no 1 0 we didn't see before actually.
1 0 1. Oh, didn't?
No.
You already know.
No, we don't have 1 0 actually.
Yeah, that's right.
So 1 0 is a 7, and then we have 1 1 1 is 8. Let's say.
I think 1 1 is at 6. Project.
What?
1 1 1 at 6.
Oh yeah.
Yeah.
Actually, you're right. So I made a mistake here. So there's no. Then that's it, right? So we have this and then this. Now let's try to encode this segment. How we are going to encode it? This kind of. It doesn't look like it will be efficient, but it will be efficient when you are compressing a long bit stream. So this one it won't be efficient. So what we're going to do is that we're going to kind of first look at the start. What should I say? First, like if you look at like what any segment, except the last bit, like of course, like the prefix, the prefix bits will be like seen before, right? So I mean, like for example, if I look at any kind of segments, for example, I look at this segment 111, except the last bit, the earlier bits should be seen before, right? For example, like this 11, I've seen it as 3, right? So therefore, like this segments here, I can kind of like compress or like encode that as a group 3 or like use the earlier index 3 and then the last bit as 1.
Oh, yes.
So similarly, like 7, I can code this as a 1 0, and this is a code it as a 3 0, and this is a 2 1, and this is a 1 1. And for this one, I would just say 0 1 and there's nothing, so I will just 0 1 and 0 0 say.
Why?
Oh no, I mean like that the word I will assume called 0 basically.
Oh,
yeah. That's you can think of like there's an empty set here, say 0 in the 0 something like.
Oh,
okay. So then like I will have like this group map into this something here, and then actually basically I'm just going to explicitly represent this with a bit stream. So of course as I go, for example, like from at the beginning, I only have one less than one group here, right? So then I only need to, let's see.
Maybe we can also try to find from the theoretically also.
What?
Find the code near to the entropy of the source.
No, here we don't need that. If this is very long, now we already kind of done, but I'm just saying that we want to convert this into bit streams. So we are going to code this into bit streams.
Yeah.
So what you can see is like basically you expect that like what going on like as we continue is like many of this group we have seen that before for most of the time, right? And like essentially like you have a very long bit stream, like something like but this bit stream I will have seen that before, and I can like instead of like sending the entire bit stream, I can just send the index of that bit stream.
Yeah, index that with the some addition. Yeah, just send that.
Yeah, so I can basically yeah, you can have many different ways to code this, but for example, like one way I can code that I can simply send the I will just assign the fixed number, not fixed number, but increasing number of bits for the number of, for the index here, the group index here. So for the early on, like for example, like for only this one here, I from here 0 and 1, I only have I only have like either 0 group or like group 1, right? So I only have like need to use 1 bit to represent like which group I'm referring to at the beginning, right? But like for example, like from 2 up to 3, so I have 4 different possible groups.
Cool.
I mean up to this point here, we already like index 4 different groups, right? So therefore like from here to here, I actually need 2 bits to represent the groups.
Yeah, that's right.
And from here to here, I will need 3 bits basically.
3 bits?
Because if I'm referring to like earlier groups, it can be like for example, like I need to, in terms of like bits like this one, 6 will be 110, right?
Yeah, that's right.
So what I mean is like, I won't have anything like 8 or 9 at this point. But it won't be sufficient if I only use 2 bits, right? Otherwise, I cannot represent like 110.
110.
I cannot refer to like group number 6, let's say. If I'm here, let's say, here I want to refer to some, for example, here I want to refer to earlier group. It can be like group 5, it can be group 4, it can be group 3, group 2, group 1, group 0. And I will need 3 bits to represent, to kind of like index all groups. Yeah.
So it means that you want to only get the 3 here, this 1, 2, and then you just leave that 1. Or so what's the result? I mean that what the result of this all?
So what I'm saying, like, what I want to say, like this, if I want to convert to bit streams here, what I can do is like, up to this point here, up to I generate group 0 and group 1, I only need 1 bit because I'm referring, I only have two groups, right? I can use 1 bit to refer to 2 groups. So I can index, I can have this index just as a 0, 1, and 0, 0. It doesn't hurt anything. Now, but afterward, I know I have 2 groups now. Like I already have 2 groups. I will need more than 1 bit to represent that.
More than 1 bit.
Because now I can have like group 0, group 1, or group 2. So I cannot just use 1 bit to. So then I will need 2 bits. So this one I will represent by 0, 1, and then 1. And this will be represented by 1, 0, and then 1.
Yes.
Now, but at this point, I say at this point, let's see. 1, 2, 3, 4. At this point, maybe earlier, maybe wait a second.
So what is the code?
Actually, even at this point, I guess.
What is the code book then?
What?
What is the code book that sent to the?
You don't need to send the code book. I mean, that's what I'm saying. Like you don't send the code book. You have this become this one, and then you want to transmit this to the decoder, right?
Yes, that's right.
Imagine you have this, you already can recover this, right?
Yeah, that's right.
Right? Well, you have this, you can recover this. So you want to send this efficiently.
Yeah.
But I'm saying like, okay, how should we send it efficiently? The last bit, it will be just 1 bit, right?
Yeah.
This is always just 1 bit.
Yeah.
But for this index, will be like keep increasing.
Yes.
And we need to be careful. Like, we don't want to use too many bits to store it and too few bits to store it.
Yes.
So one thing you can see is like, you need to increase the number of bits gradually, but that can be pretty easy to realize when you should increase that, because when you only have like 2 groups, you just need 1 bit, right? So when you first introduce this group, actually let me be careful. When I first introduced this group, I probably made a mistake here. When I first introduced this group, now here I actually have 2 groups here.
Yeah, 0 and 1.
Yeah, I'm 0 and 1. That's still okay. I just need 1 bit to store that. But after I introduce this one, I have like 3 groups, right? 0, 1, and 2, right? So I will need 2 bits to kind of like store that, right? So therefore, up to actually which one? Up to this point, I only need 1 bit. But up to this point here, I will need 2 bits.
2 bits.
Yeah.
How's that?
Because I only have like 3 groups here. If I want to refer to earlier groups, I mean from here on, I need 2 bits, right? From let's see. No,
This
actually,
one, this
yeah,
one
wait.
only 1 bit.
Yeah, this is
This
from
one?
here.
Only 1 bit.
From here I need 2 bits. I want to
Yeah.
say
From
from here
here-
I need 3 bits, right?
Yeah.
Is that right?
Yeah, that's right. From here you need two bits, and from here you need 3 bits. Yeah, that's right.
Or here? I'm not sure. Let's see.
Yeah, that's.
Uh,
I think.
yeah, you see my point anyway.
Yeah.
I think probably here.
That's
So you have like 3
bit.
groups, right?
Mm.
Wait,
That's
I
like
can't
2
here. I think it's here.
That's 1 bit.
This
That's
is
only
1 bit.
bit.
And this I have
1 0.
and 2 groups. Yeah, that's okay. Yeah, that's okay. Yeah, and then from here
So this
on.
is 1 bit, don't you think? This is 1 bit,
Yeah.
and this is from here you need 2 bit, and
Yeah.
this here you need 3 bit.
I think or like here. I'm not sure it's here. Let's see.
Why?
I have introduced here I introduced 1, 2, 3, 4 group. Yeah, it looks like it's here. Yeah, maybe it's here. So and then 3 bits I have 1, 2, 3, 4. Well, it's kind of weird, and it should be this one shift as well. Yeah, but it's okay. Like you see my point, right? Then so as long as you both encoder and decoder kind of like agree with this pattern, then at the decoder you can recover back this one also, right? Then basically then from here you can also recover back to here. So that's basically the Lempel-Ziv.
So we after that we just send this index actually.
After that you send the
Index.
bit streams, right? So
But
as-
this
let's say like I may made a mistake, but it doesn't matter. You see my point, right? At some point you just have to like increase a number of bits, right, from
Yeah.
2 to 3 and so on. So therefore here, let's say if I am correct here, I would be like this one needs 1 bit, so 0, 1. So
Yeah.
this one like 1 bit like 0, 0. This is 2 bits would be like 0, 1, 1, right?
That's 2 bit and or 3 bit.
No, 2 bits. This is 2 bits, right?
But you 1, 2, 3.
No. Here. There's a 1 here. I need to also like send this one, right?
Oh yeah. That's
Then like this one, I will, let's say 3 bits, then I will need to send a 0, 1, 0, and then 0, 1, right?
yeah.
And then this one, let's say is a 3 bits, then like still 3 bits, let's say, then it's 0, 1, 1, 0, and so on and so forth. I probably made a mistake here, but you see my point, like,
Yeah. That's right. And
then I,
it will be reduced.
and the decoder, yeah, if this is very long, it will reduce. If you're only like coding like this sequence, it will increase. But if you are coding like at least 100 bits or like 1,000 bits or 10,000 bits, then that will decrease.
Oh yeah, because something like this, we always use this
Yeah.
3. So
Yeah.
this will be
You
Yeah.
kind of like always
Yeah.
reduce the kind of like represent like a long sequence by just an index, right? And this
Yeah.
the size of the index will basically lock something, right?
Yeah, that's right.
So therefore, like it's actually it's like kind of
yeah, the more we find this one is always a repetition. Those
Yeah.
three, so that will be more decrease.
yes.
That's right.
Yes. So anyway, we should take a break. Let's just stop here and like maybe like 15 minutes break and then
Okay.
come back. Let's say like 4:40, something like yeah.
And we can find many